So I'll just quickly review what we did last time. So the equality function where Alice and Bob both have strings of length n, and they need to determine if the two strings are equal. And we showed that the deterministic complexity, communication complexity of the equality function, I said n, but actually it was n plus 1 because of the way I defined the protocol, and there was also a lower bound of n plus 1. Yes. And then we talked about randomized communication complexity. And there were two kinds, the private coins and the public coins. And we saw that any public coin protocol can be converted to a private coin protocol with an additional investment of log n bits in communication. This was Neumann's theorem. And we examined the randomized communication complexity of the equality function in the two models. So in the public coins model, and we could drive down the error to something like 1 over 2 to the k with k bits of communication. Whereas in the private coins, let's say, yeah. And so I said that this is actually tight. There is a lower bound of log n, even with constant error probability. Okay, so what we write here is the probability of error, and the superscript tells us whether we are in the public coin model or the private coin model. Okay. Then, yeah, so this is what we stopped with. That is, Alice and Bob have two strings, and they differ. That's the promise. And they need to communicate in order to determine the leftmost position where they differ. Okay. And there was a naive protocol by repeatedly using equality, and we saw that that had communication complexity something like log n times log n. The second log n was essentially there to drive the probability down, but you could somehow set up a tree walking algorithm, and that algorithm worked better, and we were able to show, let's say, for, I'm just going to call it leftmost, was actually order blocking. And it doesn't matter what is private or public. Let's say private, and let's say the error is less than. So after the talk, many people asked me about this, and yeah, thank you for asking. And of course, the reason you asked me was there were the presentation was deficient, but I'm very encouraged, and I'm going to change my plans today. So I was planning to tell you some general things about compression, etc. But instead, I think everybody likes a concrete example, and I'm just going to tell you a lower bound for what's called the disjointness function using the information complexity method. Okay, so I'm going to tell you what the disjointness problem is. It's a very important problem in communication complexity. It has many applications, and my plan is to come back on Friday and show you how disjointness means many things. Okay, so yeah, what's the disjointness problem? Alice and Bob. Alice has a subset, and Bob has a subset, and their task is to determine if S intersection T is empty. Once again, so when I say that Alice has a subset of 1 to n, we could think of Alice's input as the characteristic vector of this set, and Bob's input as the characteristic vector of the set T. And they need to communicate in order to determine if there is a position where they both have 1. Okay, that's the complement of this problem. That is the set intersection problem. Okay. And if they don't have any such position where they both have 1s, then we say that the sets are disjoint. Yeah. So let's see. Deterministic complexity of the set disjointness problem. So if you consider the following special inputs. So we give a set S to Alice, and to Bob, we give exactly the complement of that set. Okay. So the number of such inputs is 2 to the n such inputs. And the claim is each such input resides in a different rectangle. Okay. So for example, if there were two sets, S1 complement and S2 complement, and they had the same transcript, then you could cut and paste and show that there is an input where the two sets are actually intersecting, and they still have the same transcript. But of course, intersecting sets and non-intersecting sets are required to give different answers. Okay. So it's very similar to what we did for the equality function. For equality function, we showed that all the inputs which reside on the diagonal, okay, they must have their own private transcript. They cannot share transcripts. Okay. And as a result, there was a large number of leaves in our protocol tree, and since the protocol tree had many leaves, it had to be tall. Okay. The same thing happens here. We have 2 to the n such special inputs, and each of them requires a different rectangle. Okay, so I'll not carefully argue why they must have different rectangles, but you can check that. Yeah. So this looks, for the moment, yeah. deterministic complexity of disjointness of n, you can say n plus 1. And of course, we can always solve any problem by one party sending the entire input to the other. So in the case of the equality function, there was a dramatic drop in communication when we went from deterministic to randomized. Okay. And so far, our deterministic lower bound looks pretty similar to the lower bound that we used for the equality function. But it turns out that for disjointness, we don't have such efficient randomized protocols. And in fact, there's a theorem of shows that the randomized complexity, let's say even with so this is 2004. I'm not very sure about it. So yes, there was the original proof of Kalyanasundaram and Schnitger, and it was based on Kolmogorov complexity, which is information theory in a certain computational way. And then this theorem, this proof was simplified by Rasborov, and it was really put in a completely information theoretic framework, okay, by Baryosef, Jairam, Kumar, and Shivakumar. And it is this proof that I'm going to describe today. Okay, so our goal today is just to understand this. Why is it that the disjointness function, even with randomization, needs linear amounts of communication? Questions? So I really would like people to ask questions. I mean, so I really like this theorem and this approach, and I just hope that you also like it at the end.
So do you want to say private or public?
It doesn't matter, but right now let me assume that it is private. Thank you.
And this, the size of these sets?
Yeah, so we at the moment don't promise anything about the size of the sets. They're allowed to, so they are just been told that they will receive some sets and they need to find it. There are versions of the disjointness function which have applications in various areas, especially data structures, where to control the size of the sets is important, okay? And then we get other bounds. Again, many of those techniques are based on information theory. But we'll just see this today. Yeah. Questions? Yeah.
So yesterday it was 1/2. Why is it now 1/3?
Sorry.
So yesterday you started off with saying that you could get 1/2, then you can get 1/2 to the power of k, right?
Yeah.
So why is it now becoming 1/3 here? Why not just write down 1/2? Does it matter or not?
Yeah, so 1/2 is, so if I write 1/2, I mean, I shouldn't have written 1/2 yesterday either, because you can always get any problem right with probability half without communication by just tossing a coin, okay? But that was 1/2 in a special way for inputs which were equal, okay? We made no error at all. and inputs which were unequal were caught with probability half. Yeah, it was a one-sided error with 1/2, which we could amplify, and we could reduce the probability of error. Okay, so let's say that on every input, your probability of error can be at most 1/3. Very soon, I'm going to make it worse. We'll see. Yeah.
So this 1/3 is on every input.
So a randomized protocol means given any input, the two players play, they reach a leaf, and they give out that answer. That answer should be correct with probability 2/3 for every input. Okay. Yeah. So, question?
Just to look at, is this going to be a one-sided error also, or is it going to be two-sided?
We will, since it's a lower bound, we'll proudly prove it for two-sided error too.
Is it? So just a little bit different, but so here your criteria is always randomized protocol, but worst case on the input, right?
That's right.
Does it make sense to also look at a probabilistic input? So for example, S and T are randomly chosen subsets.
That's right. So, yeah. Now then the complexity will start depending on the distribution you use. Okay, so there is something called the distributional complexity, and it is closely tied to randomized complexity using duality. Okay, and that is the traditional way of showing lower bounds for randomized complexity. Okay, but we will talk about distributions on inputs, but distributional complexity will not explicitly play a role in today's proofs. Okay, but yeah, so that is a very important way of thinking about problems, especially randomized communication complexity, and I expect maybe tomorrow we'll see some of it. Yeah.
Because that would be what a sort of a classical information theorist would think of, right? The source
Yeah.
is coming from a certain distribution.
Yes.
You want to find a capacity in terms of that distribution also.
That's right. So here we are the worst case, yeah, and we want a protocol, yeah. But very soon, yeah, I think it will reach your comfort zone. Yeah.
It's okay. I'm comfortable with this also. I'm more comfortable with this also, but I'm just.
Yeah. So yeah, n equals 1. Okay. So Alice and Bob have instead of thinking of them as sets in a universe of size 1, I'm just going to think of Alice being given a bit and Bob has been given a bit, and they need to compute. They need to check if both of them are 1 or not. So I'll be switching between disjointness and intersection. Okay, I mean, if you compute and A of B, that means the two sets intersect. Now, okay, so we'll try to analyze the communication complexity of this problem. I mean, it almost looks silly. I mean, you have to send at least one bit, yeah. And what more is there to say? Okay, yeah. But the main attraction of information theory for us is that you can also say things like half a bit and 1/4 of a bit, yeah, and things like that. And what we will actually prove for this baby problem, the problem of n equals 1, is that you need some amount of information to be transferred from Alice to Bob. Okay? And how much information Alice sends to Bob will depend on the error she's allowed. Okay? So right now, we are going to be really harsh. We are going to say, solve this problem with probability of error less than half minus epsilon. Okay? So we are now analyzing the AND function. Alice and Bob both have bits. They need to compute the AND of the two bits. And they need to design a protocol where they get the answer right with probability just a little bit over half plus epsilon. Okay? And we want to understand how hard this problem is. So, yeah, they have their protocol tree, and at the end they reach a leaf, and they declare either 1 or 0. Okay. So, by MAB, I mean the transcript on input. That's the leaf that you reach. Now, they're trying to just compute A and B, the AND of A and B, but we allow them to have a huge protocol. Yeah? But what are we trying to measure? Okay. So, we'll show the following. That in any protocol which achieves error less than this, the following is true. So what am I trying to say? You give Bob the input 0 and vary Alice's input. So when I write capital X here, X is uniformly distributed bit, which is 0 or 1. Okay. Now, a particular transcript results. That means when Bob is given 0 and Alice is given X, a certain distribution on leaves arises. And when Alice's input is changed from 0 to 1, a different distribution perhaps arises. Okay. And if the two distributions are very similar, that means Alice has not leaked too much information about her input, because looking at the transcript, we are not able to guess what she had. And similarly, we are looking at the situation where Alice has a 0 and Bob's input varies. And we're asking, how much information does the transcript have about Bob's input? Okay. Now, these are, so I want to spend some time on this. These are inputs in which the value of the function they're trying to compute is known. Yeah. And is 0. Okay. Now, if and is 0, now, so let's say Bob has a 0. Is it necessary that Alice give any information? She knows that the answer is 0. Well, this is a protocol that is correct on all inputs, okay? Even 1, 1. But we are just going to analyze it on these special inputs, okay? This is not so strange. If you look at the deterministic complexity, that's what we did. We analyzed the problem only on inputs that were disjoint. Yeah? I mean, for all of them, the answer was the same. Okay? So we're doing the same sort of thing here. We are analyzing this problem on inputs for which the answer is known, the answer is 0. Okay. Now, I just want to tell you why there must be some sort of a lower bound on this information complexity. So suppose it was the case that this is very small. That means when Bob has a 0, Alice's message doesn't depend on her input. Yeah? Whether you give her a 0 or a 1, she roughly sends the same thing to Bob. Okay? All right? Now, let's see what Bob does. When Alice is 0, Bob will not give different responses to Alice. Okay. Now, suppose that is the case. Now, suppose we give both parties 1. Okay. Imagine, suppose this number was very small, and now we give both parties 1. Alice's first message, now she's worried. Maybe Bob has a 0. So I should not reveal too much information. So Alice's input is the same. Alice's message will not depend on her input. Meaning it will not vary with her input because she hasn't yet learnt that Bob has a 1. But having received this useless message from Alice, Bob cannot give too much information to Alice either because from what he can tell, Alice has a 0. And this protocol will not go too far. Even though they have 1, the transcripts will continue to look as if they both had 0s. Okay? And then, but we know that in the case of 2 0s being given and 2 1s being given, the distributions must differ significantly because in one case the answer is supposed to be 1 and in the other case the answer is 0. Okay? This is the rough intuition and this can finally be proved as this lemma. Okay. So now I'm just going to sort of put this away and let us say we believe this and turns out that the main proof. Yeah, question.
Just one question. So we're assuming private randomness here.
That's right.
In this calculation.
That's right. So again, so x is a random variable by design. We are going to choose it 0 or 1. This m is a random variable for various reasons. Okay? I mean, it varies for various reasons. One is because x itself varies. The other is that Alice and Bob somehow have this urge to use their private coin tosses to do different things, even though their input is fixed. Okay. So, yeah.
One question about the notation. So the I.
Yeah. So yeah, so the mutual information between a random variable x and n is entropy of x plus the entropy of m minus the entropy of x. M. We might as well write it as h of x minus h of x. So, how much information, how much does the entropy of x drop once we condition on m? Okay. Now, this also, for some reason, is the same as so. Here we are using that. Sorry, something wrong.
So in this lemma,
Uh-huh.
something on m other than just being a random variable, because the lemma never assumes that you know the value of m11. Right, so somehow the entire.
Oh, sorry. This m is the transcript of this protocol, and this protocol computes the and for all inputs.
And I'm saying that this lemma sort of uses the fact that m is a transcript, right?
That's
It
right.
uses the structure because that m on 00 and m on 11 must be different, right?
Yes.
The question is, what essential property of m are you actually using in this lemma? Does it have to be a transcript, or could this be true for a more general family of random variables, somehow taking into account that m on 11 should be different from m on 00?
No, so we will prove this lemma towards the end, yeah, and then let's first see what is used here. At the moment, it uses at the moment just the property that the rectangle property of protocol. So it depends very strongly on the fact that this m is a transcript. All right, so what's the plan? The plan is to now do general n. So we did n equals 1, and already I had to wave my hand so much. And yeah, so it turns out that what we will do is the following. We will show that, yeah, so let me just. The plan is this. We'll say, okay, take any protocol for the disjointness function. And let's say the protocol solves the disjointness function with probability of error bounded away from half minus epsilon. Okay. And it has communication C. Now, this is a protocol which works on n-bit inputs. Now, using this protocol, we'll show that there is a protocol for just the AND function. And this AND function the protocol for the AND function will be set up just to satisfy what we needed here. That is, it will continue to have small error. And we will not be talking about communication. We will show that this protocol achieves small error without leaking too much information. If the original protocol was efficient, then the information leaked in this protocol is also small. But we know that no protocol, no decent protocol for AND can get away with small amount of information leak. So we will just compare this with epsilon squared, and we get our own. That is the plan. So, yeah. 2 steps. One is, how is this reduction achieved? And then, why is this true? Okay. Question. So now I'm first going to do this, and then, question.
What about the first step?
Sorry, when I said this, I meant this. I thought, so this is already.
Yeah, no, but he's pointing there.
Sorry, I meant, sorry, this.
You're not waving your hands enough.
Yeah.
Yeah, I'm not.
What direction?
Sorry.
Protocol. Yeah.
So, here. So you're looking for distributions on inputs, I'm giving you 2 to the n of them. Yeah. So fix a particular protocol for the disjointness function, and we test it against various distributions. Okay, so I'm going to tell you how this distribution is set up. So there will be something called sigma, which indexes the distribution. So sigma will be a string in AB to the n. Okay. So there are 2 to the n such strings. For each of them, there is a distribution. So there are 2 to the n such distributions. Okay. Now, how does this sigma determine the inputs for Alice and Bob? Okay. So sigma is a sequence like this: A, B, A, B, and so on. Okay. So let me just call this the activation pattern. Okay, it's never been used before. I'm just making it up. Yeah, activation pattern. Yeah. So if it is A in the first position, that means Alice's input is chosen randomly as 0 and 1, and Bob's input is 0. If it is B, then Alice's input is random. Bob's input, sorry, what did I say? Bob's input is random. Alice's input is 0. Two A's and then a B. In each coordinate, one player has an active input and the other player has 0. Okay. Again, suffers from the same sort of deficiency. That is, on every input that is going to come up in this distribution, the value of the disjointness function is determined. The sets that are being generated are disjoint. Why? Because one of them is committing to a 0, and no matter what the other fellow's input is, it's never going to intersect. Is this clear? So, yeah. So such an input, I'm going to call this x sigma and y sigma. So, yeah. So x sigma is this vector, y sigma is this vector. So, all right. And we feed this to our protocol. Okay. And we look at this quantity, I of mutual information between Alice's input and the transcript. Now this quantity, so the mutual information is at most the entropy of M, and for us M is a C-bit string. This string. I'm just going to write M. It's understood that, okay, so maybe I should. So the amount of information that Alice leaks about her input in the message M, yeah, it's all bounded by C. Okay. And we have a similar inequality for Bob. So if we take the average.
Sorry, you're using the independence.
Good. Yeah, so here, for this to be true, notice that once we're talking about a fixed sigma. In this sigma, the xi's are all independent. And when the xi's are all independent, this inequality holds. Okay. We get this. So let's say this is less than or equal to C. And similarly,
The other way. We'll do it the other way. When you condition on xi minus pass, and it goes up and it's 0, and so it should go the other way. So you're either claiming equality or.
But it has a minus sign, right? So the mutual information. So the conditional entropy has a minus sign in the mutual information.
I made a mistake.
For mutual information, it's correct.
No, I think it's. Well, if this is wrong, I'm good. So, yeah.
If the xi's are independent.
If the xi's are independent, the h of x sigma will split exactly as equality, and the negative term is where you get the additivity. I think it's all right. Yeah. Anyway, I'm sorry, what am I doing? Check this. Oh, sorry. So fix a protocol with communication C. Okay, so and then I want to show this. Okay, so it is this implication that we are working on. Okay.
Yeah.
Question?
I agree with Chandra. I also think it should be the other direction, right? Because when you expand with chain rule and you get the xi's and the conditioning, then by independence you can bring them in on the right-hand side, and then you get.
Okay, so let's see. x1, x2, xn. Yeah. So sorry, this is mutual information. Then x1, x2, xn minus h of x1, x2, xn given m.
Yes.
Yeah, and this is the sum of the h of xi's. Yeah, and if I replace this by summation h of xi given m,
That's correct.
then I write this.
Yeah, that's correct.
Okay, so yeah, at least one person agrees. So it's okay. Just check, something wrong. Huh?
Here will stand for m sigma y sigma
Yes, 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 yes. So maybe I should.
sigma true at least.
Yeah. So if I put a sigma, you will assume that it was meant to be. Yeah. But yeah. So whenever there is a sigma around, assume that it is x sigma and y sigma that are being fed into the protocol, and their transcript is being examined. So, so we have these two inequalities, and just I'll divide by n and start writing this as expectation. Yeah, so expectation over the choice. Maybe I should not mess this up like this. Yeah. Okay. So expectation over the choice of I x sigma I colon m sigma plus expect y sigma I colon m sigma is less than 2c.
So can I ask a quick question?
Yes, of course.
It looks like both your lemma and everything you said so far can be actually replaced with, instead of m, you just talk about leaf of m.
Yeah. So leaf and transcript are the same thing, because in a protocol the leaf determines. Sorry, I should have just said one thing. I mean, I've said both leaf and transcript, but as far as information is concerned, one determines the other. Yeah.
Yeah, I don't know.
But thank you. Yeah, question. Yeah. So this is true for every sigma. So if I put this is still true. And whenever you see two expectations, you should expect to switch them. Yeah. And so we write expectation over I, and then expectation over sigma of m sigma So this expectation is bounded by 2c over n. So there must be, implies that there exists an I for which this quantity is bounded by 2c over n. Okay. Now that is the weak coordinate. Okay. So let me just wave my hands now. Okay. But we'll get back to concrete things very soon. So what are we looking for? We have this protocol for the disjointness function. We have done some calculations, and we have found a coordinate I, where it looks like the communication is not paying too much attention to the ith coordinate. Yeah. So now any disjointness function is a bunch of ands. Yeah? You want to know whether the and of this bit and this bit is 1, whether the and of this bit and this bit is 1, and if even one of them is 1, the two sets intersect. Okay? So what we have done so far is found one weak coordinate. Okay? What we are going to do is, there is this, let's say, little Alice and little Bob, who kind of play with tiny inputs. Okay? We are going to embed this problem in the ith coordinate and somehow use what we have just proved here to conclude that, that this is true. And don't take my constants. I leave a space here for the constants. Yeah. So yeah, but never fill them up. Yeah. Okay. So yeah. So there will be 2s, there will be 4s, and various things. Yeah. But we will have proved that we have found a protocol for the AND function where the corresponding information is bounded by C over N. Okay. So let's do that carefully. Yeah. So we have fixed an I. So should I call that I hat? Yeah.
Sorry, another question.
Yeah.
It looks like it would work for public randomness too. Did we ever use,
Yeah, so
there's some global correlation, but it's okay.
we need to be, so public randomness will work, but then here I will have to add the shared randomness explicitly. Yeah, no, there's, yeah, so just keeping it simple with private, that's all. Yeah.
I see. But the theorem and the proof is just for public.
Yeah, in any case, we know that we can translate public to private with an additional log n and we have fixed this I hat, and this has gone away, and this quantity is bounded by 2c over n. Okay. Now, what is this expectation over sigma? Let's look at our inputs. So this I hat has been chosen, and this is where eventually A and B are going to come and sit. And then there is the sigma, which tells us who's got the active input in each coordinate. Okay. Now, this sigma tells us who's got the active input in the first coordinate, the second coordinate, third coordinate, etc. Now, the sigma I can think of as consisting of sigma I, that is, who's got the active input in this, I hat. Can I just leave it as I? Yeah, the I and sigma minus I. By sigma minus I mean who's got the active input in the remaining coordinate. That's what sigma minus I tells us. Is this clear? So now this is an expectation over everything, so I can also fix sigma minus I. Okay, so let me just say that here, so for one value of sigma minus I, this quantity is still true. So let's say in the first coordinate, Alice is active. In the second coordinate, Bob is active. In the third coordinate, again, Bob is active, and so on. Now, in this, I've still not done anything. So what we know is that expectation over sigma I, yeah, the others have been fixed. The two sigma plus I y sigma I m sigma is less than C over. Now, if you compare this quantity with this quantity, yeah, what does this mean? This says, okay, so, all right, I'll come back to this comparison. Our goal was to extract a protocol for the AND function. Okay, so here's my protocol for the AND function. You've been given this input, and here was this protocol where Alice and Bob were waiting for their big inputs. Okay, this is the protocol for disjointness, okay, with communication C. Yeah. Once you're given this A and B, what you do is in the ith coordinate, which I, the special I that was found, put A and B. Okay, and then in all these places, you fill it up using sigma minus I. Okay, that is, give 0 to one of the parties, and the other party, you just toss a random coin. Okay, so this particular input can be generated by Alice herself. She doesn't need cooperation from Bob because that sigma minus I has been fixed. And similarly, this particular input can be generated by Bob. He feeds it, sorry, they both feed this input into this big protocol. The protocol runs. It's a protocol for disjointness. It doesn't know that it is being made to work so hard to just compute an AND of 2 bits. Let it run, and then eventually it gives an answer. You declare that to be the answer. It's a protocol on 2 bits. Now the question is, does it compute the AND function correctly? Well, the original protocol was computing the disjointness function correctly with probability half minus epsilon. There is no question of intersection in the other coordinates. And if A and B are both 1, then the 2 sets intersect. Otherwise, they don't. So let you confirm that this protocol computes the AND with probability half minus.
Yeah, I'm almost convinced, but there's still, the error of the original was, small, but then you picked a special I, did all these other things, so doesn't that affect the error?
Yeah, so I've always been working with expectations. Okay, so no, so at the moment, this is so I've done nothing to the original protocol. This is all in analyzing the properties of this AND protocol. I take the original protocol, I feed it, give it an input. It is duty bound to give me the correct answer with probability half plus epsilon on every input. Yeah.
Okay.
So this is a particular input.
You just run the original thing with originals.
All this is calculation. Yeah. So the protocol doesn't. Yeah. Question.
So when you fill in, when Alice and Bob plug together and they decide on a sigma,
Yeah.
Yes.
you're not taking that into communication account.
No. Yeah. Sorry.
They're doing the original.
That's right. So Alice and Bob, they were given this protocol, they sit, they analyze, they find out, this is the weak coordinate of this protocol. Then they say, okay, what sigma minus I should we choose? They do this calculation, they found out, there is a sigma minus I. They hardwire this into their system, then walk and receive their inputs little a and little b, which I have erased, and then, little a and little b. They plug it in here. They just had this fixed sigma minus I, use that to fill up the rest of the input, and then start off the big Alice and big Bob, who actually are meant to compute disjointness on n-bit functions. But nevertheless, whatever answer they give, they declare that to be the answer for the AND function.
Now, is it obvious that it's mx comma 0?
Sorry?
Obvious it's mx comma 0. This is
So, all right. So, but at least, okay, so there are many things to prove. So this computes the AND with error probability half minus epsilon. That is all right. Okay. Now, does this inequality have anything to do with this inequality? That's your question. Yeah. Okay. So what does this inequality say? Okay. So by the way, what sort of a protocol is this? All this is going to be treated as private randomness of Alice. It was input for the big Alice, but for the small Alice, it is private randomness. And similarly, this part is private randomness. There might be more private randomness which the original protocol itself had. Is that a question?
Is the rationale for Alice needing to use a private randomness, is that like a standard for channel noise?
So is that
like a standard for channel noise? Like, why does Alice need to use her private randomness?
so where? In this? here. Why is she plugging in private randomness here? Why doesn't she go with a fixed input? Is that what you're saying?
I guess for the small and problem,
Yes.
this is such a stupid question, but why not just say, oh, I have 0, oh, I have 1, okay, so not and. Why use private randomness to solve that problem?
In that case, Alice will be leaking a lot of information. Yeah? So if she just declares her input. Okay? What we are saying is that if you had an efficient protocol for disjointness, you can cook up a protocol for the AND function which is information efficient. Okay? It's still, communication-wise, it's a huge protocol. I mean, it's embarrassing to have such big protocols to compute AND function. But we are not counting communication, we are counting information. Okay. All right, so yeah, let me just go back to your question. What is this? This says if Bob is fed 0, what is the amount of information about the bit X, which is a single bit, and the transcript. And look at this contribution here. So what does this count? So when we fix sigma minus I and we vary sigma I, half the time we are counting this contribution and half the time we are counting this contribution. So actually we will have proved this, this inequality with a further factor of 2. So it's actually 4c over n. I'll let you check this. It needs a little bit of thought. So yeah. All right, so this is how we show that we can embed the AND function for 2 bits into the disjointness function, and if only we could prove this lemma, we'll be done. Okay? So I'll take a couple of more minutes and quickly tell you why this lemma is true. Questions? I mean, questions about the strategy. Okay, so what did we do? I'm saying the same thing again and again. We had a protocol for disjointness. We ran it on these 2 to the n distributions of input, and then we isolated a particular sigma minus I, and so that Alice is not leaking too much information about her input. Now, what's the point? Alice has a small message to send of C bits, and she's being distracted by all these inputs that are varying. It couldn't be that she's conveying information about all of them. They are independently varying. A small message cannot convey information about a lot of varying inputs. In the same way, Bob has a lot of varying inputs. And our calculation shows that there must be a coordinate that both of them are neglecting in their disjointness protocol, and that will lead to a contradiction. Okay. All right, so why is this true? So I think, before anybody can find further faults in this.
Erase all trace.
Yeah. So it's recorded? Yeah.
That's recorded.
So let me just, what's happening? We are analyzing the baby problem, n equals 1. Okay, Alice could have 0 or 1, Bob could have 0 or 1, and when Alice has 0 and 0, there is a certain transcript, that there is a certain distribution. So they have a big protocol tree, but the inputs are just single bit inputs. And when this input is received, namely both get 0, then a certain distribution on leaves is generated. And it is a distribution on leaves because it's a randomized protocol. Yeah. Similarly, here you have 0, 1. Now, when Bob has a 0, Alice doesn't reveal too much information about whether she has a 0 or a 1. I mean, that is the content of this being small. Okay? So if this quantity is bounded by, let's say, delta, and this quantity, let's say, is also bounded by delta. If this quantity is bounded by delta, then this distribution and this distribution would look roughly the same. Okay? Similarly, when Alice has a 0, Bob does not reveal too much information. So these two are very close. Okay. That is because this is. So now we have to work with the right distance measure. So it turns out that a good distance measure to use here is the Hellinger distance between distributions. Okay. So yeah, maybe next time if there is interest, I'll tell you. Yeah. So these two are close. These two are close. They're close by about something like square root delta in some distribution. We can quantify that. Now, by triangle inequality, these two distributions are close. So the set of transcripts, the distribution on transcripts generated when this input is given and this input is given, they're the same. Okay, so sorry, these two distributions are very close. Now, there is this little. It turns out, okay, so how do we measure distribution? So you have, what's a distribution? It's a probability vector, P1, P2, so on till Pl. If there are L leaves, now we actually just put square roots on all the Pi's so that it becomes a unit vector. If you square and add them up, it's 1. Yeah. Now, so basically, we are representing every probability distribution as a point on the scale. Okay, and the distance, the Hellinger distance, is roughly the distance between these two, and you can imagine that this distance is closely related to the dot product. So if two distributions are close, their dot products must be large. Okay. So these two distributions have large dot products. Okay. Now, because we are talking about transcripts, it turns out that the dot product of these two distributions is exactly the same as the dot product of these two distributions. Okay, so but just accept this on faith. Yeah, the dot product on these two distributions of this distribution and this distribution is exactly the same as the dot product of this distribution and this distribution. Okay, after taking square roots, which means that these two distributions also have high dot product. That means they have small distance, which is what we wanted to prove. If it were the case that this distance is small, then this distance will be small, which means this distance will be small. And if this distance is small, on the input 0, 0 and 1, 1, Alice and Bob are roughly doing the same thing. They are not allowed to do the same thing. Because in one case, the answer is 0. The other case, the answer is 1. Okay. I'll just tell you why you might expect the dot product to be the same. If you look at a particular leaf and ask, what is the probability that a protocol, so fix an input X for Alice and Y for Bob, what's the probability that the protocol gets here? It's a product of two numbers. Okay, so yesterday we checked that the inputs that reach here form a rectangle, and today all right, what's the probability that you reach here? Well, there were Alice's coordinates, and in those coordinates, Alice should go in the right direction. Okay. And then there were those places where Bob had to take an action. Yeah. So the probability or let's say tau 0, 0 of L is actually a product of what's the probability that Alice would like to go down this path whenever she's given a choice to decide? And what's the probability that Bob will go down this path? And so these numbers have this product form. There's a contribution from Alice and a contribution from Bob. Okay? So 0, 0 has a contribution from Alice, a contribution from Bob. 1, 1 has a contribution from Alice and contribution from Bob. Now, if you just rearrange those contributions, take the 0 contribution of Alice and 1 contribution of Bob, you get this. And you take the other pair, you get this. And it will turn out that this is, I mean, if it's an equality, so it can't be very deep. Yeah. Okay. So yeah. So just yeah, yeah, manipulate it and figure it out. Okay. All right. I went over time. I'm very sorry. Yeah. So I can answer questions, but this is all I have to say at the moment.
Any quick question?
So is the epsilon square tight?
No, it's not tight. Sorry, that's another thing. So there are more sophisticated versions of this argument. Sorry, this epsilon squared, I don't know. The main bound for disjointness with half minus epsilon, it's epsilon n is known. Okay, instead of epsilon squared n. Yeah, question.
Why didn't you consider the mutual information between x and y directly?
Between x and y.
Mutual information between x and y.
Yeah. So, yeah. So actually, the way it is set up, there is no single probability space in which both x and y live. This quantity is computed.
But you can define one.
Yes, but in that case, I mean, x and y are independent, so the mutual information.
If the protocol ties the two together at the end of the protocol.
Oh, at the end of the protocol. At the end of the protocol.
So wherever you have a 1,
yeah,
you learn something about the other person's identical coordinate, since there are.
Whenever there is a 1, we know that both parties have deterministic inputs 1. Oh, because it's a randomized protocol, we learned something. Okay. Yes, I need to think.
From one point of view, it looks obvious that the complexity should be order n. Because wherever you have a 1, you learn what the other person has. And you have a linear, a proportional, a number of ones which is proportional to the length of the sequence.
Yeah, so it sounds convincing. I just want to know why this is different from equality. In the equality case also, they have n-bit inputs. And yeah. So I just need to know because.
That's the second question I wanted to ask you.
Sorry. I only asked for a question. Yeah. Okay.
Any more questions? So one quick question.
Yes.
So the flavor of this proof seems a bit kind of close to classical information theory, which is you're dealing with a communication problem, for example, over a very long block, many symbols, n large. But then at the end you reduce to a single letter characterization, which is what happens about one channel use. Is there some deeper?
So there are these problems, the direct sum problems, where you have a certain complexity for a single version of the problem, and then if you try to repeat them, is it true that the communication complexity scales linearly with n? And these are questions that Sahar will talk about tomorrow. Yeah.
Yeah, I think what they call direct sum we call single
Different
letterization.
letter.
It's exactly the same.
Okay, we should have a board to write down these translation
Yeah.
in language.
What we call Hellinger was the Bhattacharya parameter.
Bhattacharya parameter, right, sorry.
The Hellinger thing which
It's a
Jaikumar mentioned
Bhattacharya
is the
parameter.
Bhattacharya.
Oh, it's a Bhattacharya parameter. Got it. Okay, now we're in comfort zone.
Sorry, okay.
Okay.
Sorry.
So let's take a little break. Thanks.